Welcome to this talk on abstract polynomial process. It is based on joint work with Fred Band and Niels de Terring. We start by saying what is an abstract polynomial process and where does it come from? So what has motivated abstract polynomial process? And actually we start with the latter. So where did it come from? So this is from the thesis from Krühner Cuchiero. There they introduced polynomial processes on RD, which is basically a Markov process, with the following invariance condition that the condition expectation of the polynomial of the state is a possible different polynomial of the state, where this polynomial Q only depends on P and H. Okay, so the time we condition back. This is some homogeneous property, of course. Okay, and so we want to somehow generalize this mechanic and understand what kind of implication does it have for the process X. All right, so a very quick overview. So basically this has been generalized in various papers. You can drop Markovianity, which is not really needed, even though you almost have a Markov process all the time. This has been generalized to the set of probability measures. So the process is taking the value of the process, their probability measure all the time, also infinite many spaces. And we know that Levy process has been generalized to D groups or Hilbert spaces. And sort of we want a generalization that works in all of these cases. And what you need for that is a notion of what is a polynomial. What is a polynomial? Because if you have the set of probability measure in infinite many spaces or Lie groups, this is really what is not so clear anymore. And instead of really defining what a polynomial is in an abstract sense, we instead say what kind of properties do we need, and basically we just take a set E, which will later serve as a state space, and say what polynomials on E, what do we mean? We mean a graded vector space of functions. P with a degree function, so under pointwise addition, polynomial plus polynomial, or function plus function now, is just a function again, and we have a degree function. And this gives us sufficient flexibility to understand in all situations something as polynomial. Okay, so this is where we start. And this is what we understand as polynomials, given graded vector space. And now, if you think about this action, this somehow has the condition expectation, this somehow has to be mathematized. Basically, if you think of Markov process, you had the semi-group properties, this is property 1 to 4, so this is basically motivated by Markov property, which is sort of almost there, not exactly. And the key additional property for polynomial process was the invariance property that the degree is kept. The degree of a polynomial of degree up to order n is again a polynomial of degree up to order n. Okay. And additionally, in this talk, this is what we always would pursue in this talk, locally finite is an algebraic condition. We say that this semi-group is locally finite if for every element in P, there's a finite dimensional subspace Vp, which is already T invariant. And which contains P, of course. Okay, in the paper, you will also find a topological condition, which of course is an important consideration, but for simplicity, we will now focus on locally finite only. So semi-group property, constant function go to constant function, P0 is just a set of constant function, and so on. Okay, so now we can say what a polynomial process is. For that, polynomials have to be given, polynomial action is given, so it's polynomial process with this given polynomial action, T, this semi-group thing. And the key property is now number 3. The condition expectation of a polynomial is the polynomial is now called THP again. And if the action is locally finite, then we call X locally finite as well. So this is what this is. We just give. So the summary is, so far as we give a set of functions together with a degree property, and this is what we call polynomials. Just over some set E, also X will just be a process on E, and then we have Markov process-like properties, which are encoded in the semi-group T, and the degree invariance property, which is also encoded in T. Okay, so if you have one of these, locally finite one, you always can define the generator on all polynomials. So here given by GPX, this is just the usual definition of generators, how this works. And the generator will be locally finite as well in the similar sense. And from the generator, you can recover, of course, the semigroup just by a matrix exponential, or by the series exponential. This means, of course, the K times composition of the generator G. Okay, and now to understand the structure of the process, this is what we really want. We have to go more towards the process X, not this away from the semigroup, but basically this will be in terms of the generator somehow. And what we do here is we take a subspace L of P, so some polynomials, which is invariant under the semigroup. And these will serve as linear functions. So this is our replacement for linear functions. We just understand these as linear functionals and use the natural embedding into the dual space of L. And in that sense, we can now identify E as a subset of L star. And in the following, I will, by abuse of notation, always assume that X is already a process on L star. And if we have that, and we have at least one of the following conditions. Here, some expectation is finite. Okay, regular was defined somewhere before. That means that a polynomial can be written as a linear combination of positive valued polynomials, or if P is an algebra, then actually the two latter properties imply the first. And in this case, you have that the linearized process has affine drift. So, finite dimensional polynomial process there, this was observed that you always have affine drift, and this is still true. And this formula is sort of, and M here, M is a martingale or some sort of weak martingale, because actually only after applying a polynomial P, this equation will actually become true. So P of xt is P of xt plus integral 0 to t, P of this expression ds plus P of mt, and P of m is a martingale. All right, for P in L. Okay, so just by taking expectations, the martingale part will disappear. Of course, since you can only do this P by P, this is some sort of weak expectation, but let's not bother with it. Just think of normal expectation, then the martingale part disappears. You have this equation, so there's no local martingale. This will be P by P, a true martingale. And you come to this equation, and this expectation of xt is a unique solution of this formula. This was called in the paper from Cuchiero and Svaluto-Ferro the Bidual moment formula under related conditions. Okay, and if we also think about the structure here of the process X, so affine drift, here's a martingale part. You can also say something about the quadratic covariance of the martingale, which is given in this form, so it's absolutely continuous, the quadratic covariance, or the compensator of MP times MQ. And what is this APQ guy? It's defined here. So if you think that P times Q, this will be automatically under this condition, P squared and P polynomial again by polarization. So, and if you think that degree 1 times degree 1 is degree 2, then basically you would think, degree 2, generator leaves degree 2 invariant. So degree 2 minus degree 2 minus degree 2 will have degree 2. So if you have classical degree property, this will have degree 2 again. And this is then similar to what was known before. Okay, quick summary. Definition of polynomial process based on abstract concepts. We have generalized the definition of polynomial processes. Here we spoke about locally finite polynomial processes. Dual and bidual moment formula can be recovered. And in the paper, we also have topological conditions, and we are working on various examples, which we'll hopefully include. Here's some related literature. Thank you for your attention. And I hope there are some interesting